The acceleration of a particle is a, which is 6ti minus 12j meters per second squared. At time t equals 0, the particle is at the point with position vector 3i plus 2j meters, and it has a velocity of 2i minus j meters per second. We want to find an expression for the velocity at time t. We're given that a is 6t minus 12, and the information we're given is that at t equals 0, the position vector is 3i plus 2j, so r is equal to 3, 2 when t equals 0, and also that the velocity is 2 minus 1 when t equals 0. We want an expression for the velocity at time t. We know that velocity is the integral of acceleration. So we want the integral of 6t minus 12 with respect to t. This is going to give us 6t squared over 2 plus a constant and minus 12t plus a second constant. So, velocity is 2 minus 1 when t equals 0. So 2 minus 1 is going to be, this will be 0, just leaving us with c1. This will be 0, just leaving us with c2. So we can see that c1 equals 2 and c2 is minus 1. Therefore, the velocity is going to be 3t squared plus constant 1, which is 2, and minus 12t plus constant 2, which is minus 1. We now want the speed when t equals 3. We have the expression for the velocity. Substitute in t equals 3. 3 times 3 squared plus 2, and minus 12 times 3, take 1. This gives us 27 and 2, which is 29, minus 36, take 1, which is minus 37. Speed is the magnitude of this vector. This vector goes 29 across and 37 down, and we want the third side of the triangle. So v is going to be the square root of 29 squared plus 37 squared, which gives us 47.0 meters per second, correct to 3 significant figures. We now want the displacement at time t. To get displacement, we integrate velocity. So r is the integral of v dt, which is the integral of 3t squared plus 2 minus 12t minus 1. If we integrate 3t squared, we get t cubed. Integrating 2 gives plus 2t, and we need a constant. Here we have minus 12t squared over 2, which is minus 6t squared. Take away t, and we have a second constant. We have this information, so r is 3, 2 when t equals 0. If t equals 0, we just get left with c1 and c2, which tells us that c1 is equal to 3 and c2 is equal to 2. Therefore r is going to be t cubed plus 2t plus 3 and minus 6t squared. Take away t plus 2. We now want the distance of the particle from its start point when t equals 5. We have the position vector. If we substitute in t equals 5, r is 5 cubed plus 2 times 5 plus 3 and minus 6 times 5 squared. Take away 5 plus 2. This is 125 plus 10 plus 3, which is 138. And then minus 6 times 25, take away 5 plus 2, gives us minus 153. We want distance, so our vector is 138 across and 153 down. The distance is the third side of the triangle. So d is going to be the square root of 138 squared plus 153 squared, which is 206 meters, correct to 3 significant figures.